Everyone. In this video, we're going to be going through and, or, and given probability. So take 3 deep breaths and let's make this math easy. All right. So in this lesson, we're going to look at 3 different types of probability. And the reason why we're learning about all 3 of them together is because their formulas involve the formulas for the other calculations. So for example, the first piece of notation that we're learning is that the probability of event A happening given that B happens, it doesn't really have like a formula of like how to calculate it. You just think about the process and you say, okay, well, if I assume that B happens, then what's the likelihood that A is going to happen? So that's what given probability is. And this is important because it's used in the formula to find the probability of event A and event B happening. Because the way that this is calculated is you find the probability of event A happening by itself, and then assuming that A happens, you find the probability of B. And this formula can actually be extended for multiple events. So like if you wanted to find the probability of event A and B and C as well happening, you would do the probability of event A happening times the probability of event B happening, assuming that A happened, and then you do the probability of event C happening, assuming that both A and B happened. And basically, you could extend this for however many events you have. You just assume that all of the previous events have happened, and you use that to find the likelihood that the next event happens. So that's the formula for and probability. And then the or formula uses that calculation as part of it. Because if you wanted to find the probability of event A or B happening, you would take the probabilities of each of the events happening individually and then add those together. And then you would subtract the probability of both of them happening together. So this and formula that we use here ends up being part of the formula for the or formula. So let's look at what this looks like in practice. So on this first slide, we're asked to find 2 given probabilities, an and probability and an or probability. So for the first one, if I'm asked to find the probability of choosing a red card, assuming or given that I draw an ace, the way I would think about this is I would say, okay, my assumption is that I choose an ace. So when I write out my fraction for the probability, the bottom number isn't going to be all 52 cards because not all 52 cards are aces, and I'm assuming that I draw an ace. Instead, there's only 4 aces in the deck of cards. And so the bottom number of my probability would be 4. And then the likelihood that I choose a red card, assuming that I draw an ace, is just 2 out of those 4 cards. And when you divide that out, you end up with the decimal version of the probability as 0.5. So that would be the probability of choosing a red card given that you choose an ace. And the order that you write this in matters because if you were to find the probability of choosing an ace, given that you choose a red card, well, in this case, the red cards that you're assuming that you're drawing from are like there's 26 possible outcomes, and only 2 of those are aces. And so you would have 2 out of 26, which in decimal form would be 0.07692. And that would be the probability of drawing an ace given that you draw a red card. And you can see those probabilities are very different. The probability you draw a red card given you draw an ace is 50% versus the probability that you draw an ace given that you draw a red card is like 7 or 8%. So very different there. And just remember with the given probability, you're finding the probability of the first thing, assuming that the second thing happens. Um, and so if we wanted to find the probability of choosing a red card and an ace, we would use this formula here, which says that to find the probability of two events happening together, you find the probability of the first event happening by itself. So in this case, our first event is drawing a red card. So we would have 26 out of 52, because out of the 52 cards, 26 of them are red. And then we would multiply this by the probability of choosing an ace, assuming that we draw a red. So there's only 26 red cards to choose from. Two of them are aces, and that's basically the probability we just found, because that's what we were calculating up here, is the probability of drawing an ace, assuming that you draw red. And once you have those two fractions, then you can just calculate out the probabilities. And there's several different ways you can do this. So I think the easiest way is just to convert each probability into decimal form and then multiply those probabilities together. So I do like 26 divided by 52. That gives me 0.5. Then I do 2 divided by 26, and that is 0.07692. And when I multiply that by 0.5, that gives me my final probability of 0.03846. So I think that's the easiest way to calculate them out, is to put them in decimal form, multiply the decimals, and find your answer that way. However, you can use the rules for multiplying fractions. So when you multiply fractions, you multiply the top numbers together, and then you multiply the bottom numbers together, and then you can divide those to find the decimal form. And when you are multiplying fractions, you can also cross reduce fractions, because like 26 divided by 26 equals 1. And so you could simplify that fraction to just be 2 over 52, which would also give you this same decimal. Um, and technically you could reduce that further, but I find this form of the this form of the fraction to be helpful, because essentially what that's telling me is out of the 52 cards, there's two of them that are aces, which makes sense because, or sorry, two of them that are red aces, I should say, because that's the probability we were looking for, is the probability of choosing a red card and an ace. So that logically makes sense, that that probability would be 2 out of 52. And sometimes when you're doing these and probabilities, you might not need to use the formula, depending on what the problem is, because you can just think about the problem and say, well, I know out of 52 cards, two of them are reds and aces. So you could just find it that way as well. But this formula will always work, and some of the situations you'll be given might not be so easy to just think about in your head. So basically, that's how you would use that formula. To do the next one, where we want to find the probability of choosing a red or an ace, we would use this formula right here. And this one says that you find the probability of the first thing, which in our case is drawing a red card. So there's 26 out of the 52 red cards. Then you find the probability of the second thing happening by itself, which is 4 out of 52 cards. And then you subtract the probability of both of these events happening together. So since we just calculated that in the green part, I'm just going to use my answer from there and put in the 2 out of 52 there. But sometimes you'll need to actually calculate it if you haven't calculated it in an earlier part of the problem. And just like we did in the problem above, I think the easiest way to do this is to think about them in decimal form. So like you'd say 26 out of 52 is 0.5. We're going to add that to 4 out of 52, which is 0.07692. And then we're going to subtract 2 out of 52, which is 0.03846. And when you add those together, 0.5 plus 0.07692 minus 0.03846, that ends up equaling 0.53846. So that would be the probability of choosing a red or an ace. So you can put them in decimal forms, add them and subtract them in that way, or you can follow the rules for adding and subtracting fractions and figure out what the fraction answer is and then use that to find the decimal. So if you were doing that, when you add and subtract fractions, you have to have common denominators, which conveniently these fractions already do have common denominators. And then you just add and subtract the top numbers. So 26 plus 4 is 30, minus 2 is 28. So if you were to do 28 out of 52, that would give you this same decimal that we got here. So either way works. It just kind of depends on how confident you are with fractions. If you have a hard time remembering the difference between multiplying and adding and like when you have to find common denominators and when you can cross reduce and like keeping all of those rules straight is hard for you, I would recommend just converting them into decimal forms and using those to find your answer. But if you feel really good about fractions, you can follow the rules for adding and subtracting or multiplying fractions to do that. So, oh, there was one other thing I wanted to mention. The fraction version of the calculation does provide some meaning behind how these formulas are working. Because basically, this 26 out of 52 is saying out of the 52 cards, 26 of them are red. And if I want to get a red or an ace, I need to count all of those 26 cards. And then I also have to count the 4 ace cards. And then if you look at the cards that I've circled, these two were double counted because they were counted as red cards and they were also counted as ace cards. And that's why we subtract 2 out of 52, which is the probability of choosing a red and an ace, because we basically double counted those cards. And when you add the cards together and you have 26 plus 4 cards, that's the 30 cards that I've circled. And then you subtract the 2 cards that were double counted because there's actually only 28 cards in this deck that are reds or aces. So looking at the fractions can help you conceptually make sense of it. But when you're actually doing the calculations, I think it's easiest to just put them in decimal form. So let's look at another example. And in this example, I want to show you guys why the formulas work. So in this situation, we are rolling a die and flipping a coin. And we want to find the probability of rolling a 3 and flipping a tail. So if we look at our AND formula, the way we're going to calculate this is we're going to find the probability of our first thing, which is rolling a 3. So that probability is 1 out of 6. And then we're going to multiply by the probability of getting a tail, assuming that we got a 3. And if you think through it, if you roll a dice and you get a 3, it's not going to impact the results of flipping the coin in any way because they're independent events. And so in this case, that's just going to be the probability of flipping a tail because event A, or the rolling the 3, didn't impact the second event in any way. But sometimes it will, like on our last example where we were drawing cards that were aces and red cards. But in this case, the first event didn't impact the second one. And I'm going to do this in fraction form just to connect the meanings of what the calculations are doing. I would recommend doing them in decimal form when you're actually doing the calculations, but I'm going to show you guys what the fractions show us. So when I multiply these fractions together, 1 times 1 gives me 1, and 6 times 2 gives me 12. So the probability of rolling a 3 and flipping a coin and getting a tail is 1/12. And the connection to the choice trees that you guys did on the sample spaces and choice trees assignment can be seen in this calculation, because this 1/6 is basically referring to the one outcome out of the 6 outcomes you have possible when you roll the dice. And then the 1/2 is referring to assuming that you get a 3, it's 1 out of 2 possible outcomes for flipping the tail. And when you multiply these together, you're basically using the fundamental counting principle because 6 times 2 gives you all 12 of these possible outcomes, which you can also write in sample space form here. And then the 1 times 1 is referring to this specific outcome, which was getting a 3 and a tail. Or in the sample space part, it's this outcome right here. So that's why we multiply the fractions together when we're doing and probabilities. Is because we're basically using the fundamental counting principle to find the number of possible outcomes as well as the number of favorable outcomes, which in this case was getting a 3 and a tail. So that's why the formula works for that situation. So now let's do an OR formula and look at how that works. So if we wanted to find the probability of getting a 3 or a tail, we would use this formula. And we would start off by finding the probability of just getting a 3 by itself, which is 1 out of 6. Then we would add the probability of getting just a tail, so only looking at flipping the coin, that would be 1/2. And then we would subtract the probability of getting a 3 and a tail, which we just found above was 1/12. So to find the meaning behind this one, we first need to put the fractions into common denominator form so that we can add and subtract them together. So the common denominator of all of these fractions will be 12 because 12 is the least common multiple of 6, 2, and 12. And the last fraction already has a denominator of 12, so we won't need to change that at all. But the middle fraction, if we want the 2 to be a 12, we'll need to multiply the top and the bottom of the fraction by 6. So that tells us that 1/2 is equal to 6/12. And 6 times 2 will give us 12. So that tells us that 1/6 is equal to 2/12. So this calculation is the same one that I showed above. It's just written in common denominator form. And so when I have my common denominator, I can then add and subtract my numerators. So 2 plus 6 is 8, minus 1 gives me 7. And so I get 7/12 for the probability of getting a 3 or a tail. And again, you don't have to go through this process when you're actually doing the calculations on your homework. You can just turn them all into decimals and add and subtract them. But I'm showing the fraction form because it shows the meaning of where this formula comes from. Because basically, this 2/12 is referring to the 2 possible outcomes that you have when you roll a 3, because that was the probability of just rolling the 3. So in our sample space, it's referring to these 2 outcomes out of the 12 that have a 3 as the result of the dice roll. Then this 6/12 is referring to all of the outcomes that have tails. So in our choice tree, it's referring to these branches. And in the sample space, which comes from the choice tree, it's referring to all of these outcomes. So that's where the 6/12 is coming from, is because there's 6 out of the 12 outcomes in our sample space that have tails. And then this part, this 1/12, is referring to this outcome here that was both a 3 and a tail. And the reason why we subtract it is because that one got double counted. It got counted in my 2 outcomes that had 3s. It also got counted in my 6 outcomes that had tails. And it's only a single outcome, but we counted it twice. So you subtract it to like undo that double counting. And that basically tells us that there's 7 out of the 12 possible outcomes that have a 3 or a tail. And we can see that that is true because this one has a tail, this one has a tail, this one has a 3, this one has a 3 and a tail, so it like really meets the criteria of having a 3 or a tail. This one has a tail, and a tail, and there's a total of 7 of them, and that's the answer you get when you do 2 plus 6 minus 1. So that's where those formulas come from. And you don't have to put them in fraction form. You can just do the decimal form when you're calculating them, but that's the reasoning behind why these work. So another topic I wanted to cover is the idea of all probability. So a lot of times you'll be asked to look at a situation where you have multiple events happening and you're asked to find the probability of, like in this case, all of the 4 marbles we choose being blue marbles. And the way that you want to think about this is basically like a repeated and problem, because we have the formula that the probability of A and B equals the probability of A times the probability of B, assuming that A happened. But you can extend this this formula to as many events as you want to. Like if you wanted to say, like in this case, that there's 4 marbles that we're drawing, and we want all of them to be blue, you can think about it as the first one being blue, and the second, and the third, and the fourth, because that would mean they would all be blue. And that calculation is going to be basically 4 probabilities multiplied together, where the first outcome is assumed as part of the probability of the second outcome. And then the first 2 outcomes will be assumed as the probability of the third one, and so on. So to do this, in this situation where we have a whole bunch of marbles, we first need to figure out what the probability is of the first marble being blue. So in this situation, we have 1, 2, 3, 4, 5, 6 blue marbles. So that will be the number on the top. And in total, we have those 6 marbles plus 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37. So there's 37 marbles in this whole group of marbles, and 6 of them are blue. So this is the probability of the first marble being blue. Then the probability that the second marble is blue depends on whether or not I'm replacing the marbles. So for this first one, let's assume that I don't put the marble back into this pile. So I select a marble, I get a blue one, and my second probability needs to be calculated assuming that I drew the marble I wanted to on the first one. So if I don't replace the marble that I drew, the probability of the next marble being blue is going to be 5 out of 36, because there's only 36 marbles to choose from, and one of the blue ones was the one that I took out for the first event. So that probability would be 5 out of 36. Then the probability that the third marble is blue is going to be 4 out of 35, because again, I'm not putting the marbles back in. So assuming that the first 2 are blue, the probability the third one is going to be blue is 4 out of 35. And then since I'm choosing 4 marbles, I still have one more event to account for. And that probability that the fourth marble is blue is going to be 3 out of 34. So in this case, it might be easier to use the fraction multiplication rules, because we can just multiply all of these numbers together and all of these numbers together, figure out what that is, and then divide them. And the reason it might be easier to do it in that way is because these are basically permutations, which makes sense because that would be the number of ways you could choose these marbles. So if I do 6 NPR 4, that gives me 360 for the top number, and 37 NPR 4 gives me a very large number, 1585080. And if I divide those, I end up with a very, very small probability of 0.0002271. And the reason why that probability is so small is because it's not very likely, if you draw 4 marbles, that they're all going to be blue. So that's what that calculation would look like. And if you did a situation where you were drawing marbles, but you put the marble back in every time you drew one, that calculation would be a little bit different because you would have 6 out of 37 for the probability that the first marble is blue. But then the second marble's probability would also be 6 out of 37 because you put your first marble back into the pile, which means it's still an option to select that blue marble again. So when you have these problems, pay attention to whether or not you have replacement because it will slightly change your calculations and your final answer. Because in this case, when you do 6 times 6 times 6 4 times, or you can also do that as a regular exponent, not a falling exponent, you get 1296. And then if you do 37 times itself 4 times, or you could use a regular exponent to do that, that gives you that number. And then when you divide those, you end up with 0.000691. So still really small, but you can see that this probability is bigger than this one. And that makes sense because if you're putting the blue marbles back in every time you draw one, it's going to make it more likely that the next few marbles are blue. So that's the idea behind all probability. And it's based on the AND formula. And you can multiply however many probabilities together that you need to based on the number of events that are happening. And sometimes they'll look kind of like permutations if you are doing it without replacement. And sometimes they'll look kind of like exponents if you're doing it with replacement. So that's the idea behind all probability. And on your assignment, you have one question that has to do with large populations. So I wanted to go through an example of this one. So in this situation, it says in a large population, 45% of the people have a pet. And if you randomly select 5 people, what is the probability that all of them have a pet? So we're trying to find the probability that they all have a pet. And since we're selecting 5 people, we're going to have 5 probabilities that are multiplied together. Now, the issue in this case is that we weren't told how many people are in the population. We were just told that it's a large population and 45% of them have a pet. So in a large population, we don't know how big it is. Like it could be 100,000, it could be a million. Like we don't know how big this population is, but you can think of the percentages as being a fraction of whatever the population is. So, like if we had 100,000 people in the population, 45% of that would be 45,000. So the likelihood that you choose someone who has a pet for the first person would be 45,000 out of 100,000. And then the probability that the next person you select has a pet, assuming that the first person does, would be like 44,999 out of 99,099 or 999, because the first person that you choose isn't available to select again because you already selected them. And so the probability that the next person would have a pet would be like basically just one number lower in the numerator and denominator. However, when you turn those into decimals, so if I do 44,999 divided by 99,999, that gives me 0.449999. And like the decimal goes on for quite a while. And so when you round that decimal to 4 significant figures, like I've asked you guys to do, it's basically just 45%. And that's a good thing because I wasn't told that I have 100,000 people. I might actually have 1,000,000 people, or I might have, some random number of people in this large population. And so when you're working in a large population, you can assume that these fractions, whatever they are, whether it's 100,000 people or 1,000,000 people, that these fractions are close enough to the percentage that you're given that you can just calculate this as 0.45 times 0.45 and basically just do that 5 times. because yes, the decimals will be slightly different, but you're also not given enough information to be able to figure out how different they are. And in a large population, the differences will be so small in terms of the actual probabilities that it won't make a difference in your ultimate answer. So in this case, the probability that all 5 people have a pet would be 0.45 times itself 5 times. And if you want to, you could use a regular exponent to calculate that. And that would give you 0.01845 as that probability. And this number makes sense because even though like almost half of the people have a pet, the likelihood that you select 5 people and they all have a pet is not very high. So it's about 1 to 2% likely that all 5 people will have a pet. Because most likely, if you select 5 people, you're going to get a mixture of some people who have pets and some people who don't. And so the likelihood that they all have a pet is not very high. So that's a lot of concepts. If you need to go back and review any of those, feel free to do that. After you've reviewed all of the concepts from this video, I want you to try these 3 questions on your own. So I'm sorry it was kind of hard to get them to all fit on the same slide. Basically, these questions on the left are all related to this table. So you're randomly selecting a person from this class whose favorite colors have been like separated by gender. And then these 2 questions are separate from those. So you've got like kind of 3 questions that you're working on. But the first question has 4 parts to it. And I also included the formulas up here so that you can use those as you solve them. So pause this video, try these problems on your own, and then restart it to see how I would solve it. Okay, so the correct answers for this first question are 0.5, 0, 0.8, and 0.5357. And then the correct answer for the second question is 0.00, like 2 zeros, and then 9955. And for the third question, it's 0.006147. So if you didn't get any of those questions, go ahead and skip forward to the timestamp shown on the screen to see how I solved them. Okay, so for this first question, we're randomly selecting a person from a class of 28 people. And that 28 can either be found by adding up the total number of people for each color or like their favorite colors, or you can add up the total number of people of each gender. Either way, you end up with a class of 28. And the first question is asking us to find the probability of selecting a student who is female or their favorite color is blue. So we're going to use this OR formula here. And we would solve it by saying, okay, well, what's the probability that you choose a student who's female? Well, in that case, it would be 11 out of 28. And then we're going to add the probability of choosing a student whose favorite color is blue. So there's 8 students whose favorite color is blue because of this number here. So 8 out of the 28. And then I also need to subtract the probability of choosing a student who is female and their favorite color is blue. So there's 2 ways to do this. You could use the formula for the and calculation, and you could say, okay, well, the probability that I choose a female is 11 out of 28, and then I multiply that by the probability of choosing a student whose favorite color is blue, assuming that they're female. So that assuming that the first thing happened is really important as part of the and formula. So you'd say, well, I've got 11 females and 5 of them have their favorite color is blue. And if you do the cross reducing for multiplying fractions, that 11 divided by 11 cancels out. And you basically end up with 5 out of 28, which you could have figured out just from the table because there's 5 students whose favorite color is blue who are also female. So you could figure it out just by looking at the table, or you could use the formula, but you still get 5 out of 28 regardless. And then I'm going to add and subtract these probabilities together. So 11 divided by 28 is 0.39285. So I'll round that 8 up to a 9. And then 8 out of 28 is 0.2857. And then 5 out of 28 is 0.17857. So I'll round that 5 up to a 6. And when I add those all together, 0.3929 plus 0.2857 minus 0.1786 ends up giving me 0.5 exactly, actually. And that would be my answer for the probability of choosing a student who is female or their favorite color is blue. You also could have got that same decimal if you had added and subtracted the fractions together, which in this case isn't too hard because it already has common denominators. So you could go like 11 plus 8 minus 5 gives you 14. And 14 out of 28 does equal 0.5 because it's half of 28. So that would be another way that you could get that probability. So that's how you do the first one. For the next one, if you're finding the probability of choosing a red or choosing a student whose favorite color is red and their favorite color is yellow, I'm going to show this with the formula method, and then we'll talk about how you could also like just think through it logically. Because the probability of choosing a student whose favorite color is red and yellow will be the probability of choosing a student whose favorite color is red, which is 5 out of 28. And then I'm going to multiply this by the probability that I choose a student whose favorite color is yellow, assuming that I choose a student whose favorite color is red. So that assumption that I'm choosing a student whose favorite color is red means I'm going to have 5 in the denominator of that fraction. And out of all of the people whose favorite color is red, there are 0 people whose favorite color is yellow because their favorite color is red. And so if you assume that you're choosing someone whose favorite color is red, you're not going to get someone whose favorite color is also yellow. And so in this case, you just end up with 0 out of 28 because you could do the whole cross reducing thing. And that makes sense because there's no people in this class who have 2 separate favorite colors because the way this table was made, it was assumed that you can only have one favorite color. So that can happen where you get a probability of 0 because it's impossible to have both of the things happen at once. So that's how you would do that one. And then for the probability of choosing a male, assuming that their favorite color is green, you would say, okay, well, how many students are there whose favorite color is green? There's 5 of them. And out of those, 4 of them are male. So you would have 4 out of 5. And I think that will be 80% or 0.8 when you divide that. So that would be how you would solve this one. And most of the time, we don't do given probability just by itself. Most of the time, it's done in the context of the AND formula. But sometimes you might get some problems where you just have to find the given probability. So that's how you do that one. And then this last question kind of goes back to the second question and that issue that we were looking at there. Because in this case, we're looking at the probability of choosing a student whose favorite color is red or yellow. And so the way you would think about this one, again, we're going to be using this OR formula, but we would say the probability of choosing a student whose favorite color is red is 5 out of 28, because there's 5 students whose favorite color is red out of the 28. Then the probability of choosing a student whose favorite color is yellow is 10 out of 28. And then we would subtract the probability of choosing a student whose favorite color is red and yellow, which we found out earlier is 0 out of 28 from up here. And when we added these numerators and denominators together, 5 plus 10 is 15 minus 0 gives us 15 out of 28. You could also find the decimals of each of the fractions and add and subtract them together. But regardless of which method you use, 15 divided by 28, or all of those individual decimals added and subtracted together, will give you 0.5357. And that would be your answer for that one. And in this case, this subtraction of 0 over 28 makes sense because there's no overlap between red and yellow. So you're not double counting anything. And so you don't have to, like when you subtract the or the double counting, it's just subtracting 0 because there are no students that got counted as having their favorite color as red and also yellow. So that's how you would do question 1. On question 2, it says, if you randomly choose 3 cards from a standard deck of cards, what is the probability that all the cards are face cards? Okay, so in this problem, we have 3 events, which means that we're going to have 3 probabilities that we're calculating. And the probability that the first card is a face card is 12 out of 52. Because out of the 52 cards, you have 3 face cards in each suit, and there's 4 suits, so that means you have like 12 face cards total. Now, it didn't specifically say that we are replacing or not replacing the cards back into the deck of cards, but if you think about randomly choosing 3 cards from the standard deck of cards, you're going to end up with like a hand of 3 cards, which means you're not putting them back into the deck. So if it doesn't say that you're like specifically with replacement or without replacement, you can just assume that it's without replacement because like you're choosing 3 cards from the deck. So you would say, okay, well, the likelihood that the first card is a face card is 12 out of 52. But if I'm not putting that card back into the deck, that means the likelihood that the next card is a face card is going to be 11 out of 51 because I already have one of the face cards withdrawn from the deck of cards. Then the likelihood that the third card is a face card is 10 out of 50. And you can find those individual probabilities, or you can multiply the top numbers together and the bottom numbers together, which isn't too bad because those are just permutations. So we'll do 12 NCR, or sorry, NPR 3, which is 1320, and then 52 NPR 3, which is 132,600. And when we divide those, that gives 0.009957. So we'll round that 4 up to a 5. So basically, it's almost 1% likely that all the cards will be face cards. So not very likely, but that also makes sense because there's a lot more cards than just face cards in the deck of cards. So it's not going to be very likely that if you choose 3 cards, that all of them will be face cards. You're probably going to get a mixture of face cards and non-face cards, or it's also pretty likely that you might get all non-face cards, which we'll look at in our next video. So that's how you would do question 2. On question 3, it says, in a large population, 28% of the people like black licorice. If you randomly select 4 people, what is the probability that they all like black licorice? So again, we're going to have 4 probabilities multiplied together because we're randomly selecting 4 people. And so the question is what are these probabilities? Well, the probability that the first person likes black licorice is going to be 28% because 28% of the people in the entire population like black licorice. So we know that this one is going to be, either 28,000 out of 100,000 or, 2.8 million out of 10 million. Like we don't know what the number of people is, but we know that it's going to be 28%, which we can write as 0.28. Now, the probability that the next person likes black licorice will be a fraction where the numerator and denominator have decreased by 1 because we've taken one person out of the population for our first person. However, in a large population, the numbers will be so big that when you divide them, even though they were both decreased by 1, they're basically going to equal the same as 28%. It might be 0.279999999, but it's close enough that you can just approximate it to be 28%. And by a similar reasoning, all of the following probabilities will also be 28%. So to find the probability that all 4 people like black licorice, you would do 0.28 times itself 4 times, or you can use a normal exponent to calculate that, and that would be 0.006145, which means we'll round that 6 up to a 7. So it's less than 1% likely that you're going to choose 4 people who all like black licorice in this population. And that's how you would do question 3.